Hi, my name is Yik Lung Pang. I'll be presenting our work on performing safe human-to-robot handovers of unknown containers. This work is done in collaboration with Alessio Zampero, Chanji Oh, and Andrea Cavallaro of the Center for Intelligent Sensing at QMUL University of London. Performing human-to-robot handovers of unknown containers in the real world is challenging and potentially unsafe. The robot may pinch or strike the human accidentally if the estimation of the human's hand pose is inaccurate. Moreover, fragile containers may break or deform, and the content will be spilled if incorrect forces are applied, which can cause harm to both the robot and the human. Scanned 3D object models or equipment such as motion capture systems and markers can be used to improve the estimation's quality, but they are not always available. On the other hand, physics-based simulators are particularly effective for human-to-robot interaction scenarios for several reasons. First, the interaction between the human and the robot is performed in the virtual environment, ensuring the safety of the interaction. Secondly, the experiments can be performed faster than real time, and the environment can be reset automatically, reducing the time required for data collection. Existing work on simulators for handovers either focuses on the visualization of the handover trajectory or is limited to the use of primitive shape objects or scanned 3D object models, or they only consider static or limited dynamic setups where the robot stays stationary waiting for the human to place the object in its gripper. In this work, we propose a modular real-to-simulation framework for developing and evaluating algorithms of safe human-to-robot handovers, which addresses these limitations by simulating contact forces during the handover, constructing handover objects with efficient-based methods, and considers fully dynamic setups where both the human and the robot approach the handover location together. We start from RGB videos of humans pouring fillings into containers and handing them towards a robot. The videos start from the object manipulation phase, where the human prepares the container for handover by pouring fillings such as rice, pasta, or water into the container up to various fullness. Then the human hands the container towards the robot in the human maneuvering phase, as if to perform a handover. We perform perceptual estimations using our vision-based pipeline to estimate hand poses and object properties, such as shape, trajectory, and filling mass, and combine that with annotations of the object mass to recreate the handover scenario in the simulation. In the object manipulation and human maneuvering phase, the container and human hand models will mirror the behavior in the real videos by following the trajectory and orientation estimated by the perception pipeline. The robot will approach the container location in the human maneuvering phase and perform the handover by grasping the container where it is unoccluded by the human hand. Finally, the robot will attempt to deliver the container safely to a target area behind itself. Here is an overview of the simulation environment. We have the reconstructed container head model representing each individual container. We represent the human hand using the modular prosthetic limb hand model. The safe grasping region is estimated and highlighted by a green mask on the container model, and our setup uses a UR5 arm and a robotic 85 gripper to perform the handover. However, other models can be used. Finally, we have the target delivery area behind the robot on a separate table. In order to recreate the handover scenario in simulation, we propose a vision-based pipeline to estimate hand poses and object properties. We first perform shape reconstruction of the containers. We minimize the cylindrical shape to the real object shape by constraining its projection to the object's cementation mask from two views of a wide baseline stereo camera. We then perform hand key points estimation and obtain the hand pose and joint angle of each finger joint. We segment the container in the first frame of the recording and track the cementation mask in subsequent frames. We obtain the centroid of the cementation mask as the container location, and we set the orientation of the container to be the same as that of the hand holding the container to obtain the container pose. We obtain annotations of the container and filling mass using a high-precision electronic scale and set the mass in the simulation accordingly. To control the robot to grasp the object safely, we need to specify the grasp location and orientation. We set the grasp orientation to the object orientation so that the robot will grasp the object directly from the front. However, grasping the object as a centroid can be unsafe as the centroid may be occluded by the human hand. Therefore, we combine it with the estimated hand key points, object dimensions, and orientation to estimate the safe grasping region to obtain a final grasp location. To estimate the safe grasping region, we first extract hand key points that are close to the container. We obtain an unsafe region based on the extracted key point's location with respect to the height of the container. We initialize the safe region for grasping using the dimensions of the container, and we subtract the unsafe region to obtain the final safe region for grasping. We obtain the final grasping location as the centroid of this safe grasping region. If a safe grasping region is available, the robot will approach a container and attempt to grasp it. Otherwise, the robot will stay at a distance to avoid harming the human. The robot should also avoid breaking or deforming the container by applying the minimum amount of force required to hold and deliver the object, which requires an estimation of the object mass. To estimate the filling mass, we perform joint filling type and level classification by training a convolutional neural network on selected frames of the recordings, cropped based on their segmentation mass. We obtain the filling mass at the frame when the robot executes a grasp and combine that with the annotated container mass to obtain the object mass. We then use a previously learned linear model to predict the required amount of gripper force to hold and deliver the container, which will be applied by the robot on the container. Note that other modalities such as audio can be used to better estimate the filling mass of opaque containers where the fillings cannot be seen. To compare the safeness of different algorithms for human-to-robot handovers, we define safety measures for both the human and the object. To measure the safety of the human, we use the sigmoid function, which does indicate when the minimum distance between the hand and the robot is less than a safety distance, capital L. If the human safety is low, this indicates a collision between the robot and the human, and the handover is unsafe for the human. Otherwise, if human safety is high, the robot is unlikely to harm the human. To measure the safety of the object, we use a mirrored exponential function, which indicates when the force predicted to be applied onto the object deviates from the force required to hold and deliver the object. Excessive force indicates that the object may deform or break, and filling may spill, while insufficient forces indicate that the object may slip and fall. Otherwise, a high object safety indicates that the robot is holding the object safely. Here we showcase the difference in handover safety with and without our proposed safe grasping region estimation. In the first example, the robot is able to identify the unoccluded region at the top of the container and execute the grasp accordingly, achieving high human safety. Without estimating the safe grasping region, the robot grasps the centroid of the container, resulting in low human safety. In the second example, the robot correctly identifies that there is no safe grasping region available and avoids approaching the container to ensure high human safety. Again, not estimating the safe grasping region results in low human safety. Here we showcase more example handovers with different containers and fillings. The first example shows that even when targeting to the safe grasping region, the handover can fail due to insufficient forces applied, resulting in low object safety and a dropped container. The second example shows that while sufficient forces is applied to hold and deliver the container can fall if it is delivered at an angle, resulting in spilled fillings. The final example shows that with sufficient forces applied and the container grasped in an upright orientation, object safety is high and the delivery is successful. In summary, we propose a novel modular real-to-simulation framework for human-to-robot handovers, which enables development and assessment of algorithms when the real robot is not accessible. We propose a vision-based pipeline to estimate the physical properties of an object manipulated by a person without the use of markers, motion capture systems, and scanned 3D object models. We also propose a method for estimating a safe grasping region on a container held by a person. Finally, we quantify the handover safeness in terms of human safety and object safety. Future work will include validation of the algorithms with a real setup and improving the details of the simulation with deformable objects and content dynamics. Thank you for listening.